Hello everyone, I'm back here with the question number 2 of the paper 1 of JEE Advanced. As we have been doing in the last video, we have done the very much elaborate detailed solution for the question which was based on metallurgy. Now we'll be doing the discussion of the question number 2, which is based on the Grignard reagent, and they had tested for the nucleophilic addition reactions of the Grignard and a few other concepts along with that. So this is paper 1 in continuation of the previous video. We are saying this is most elaborate solution. You can check yourself on internet, or possibly you'll not find any other such a detailed solution as we are having over here right now. And this is the part of section 1, which was one or more than one correct question. Question number 2, it was that we have got 4 reaction sequences. P, Q, R, S, these products were formed when our Grignard reagents were reacted with some cyanide, and then the product formed again with the Grignard reagent. That was the first sequence. Benzene was reacted with acetyl chloride in the second reaction sequence in presence of AlCl3, and then again Grignard reagent was used. In third reaction sequence, and this some acid chloride was reacted, and we had here some dialkyl cadmium. This is kind of a distant cousin of the Grignard reagent, a little bit different in the reactivity. And the fourth reaction sequence again started from the aldehyde reacting with the Grignard reagent as such, then oxidation by CrO3, reaction with HCN to form cyanohydrin, and then dehydration using sulfuric acid in presence of heat was there. And we were asked about the products which are being formed, where are asymmetric carbons present or they are absent. Asymmetric carbon present or not present, that was the main question. So first we'll see what are the products coming out of these reactions, and then we'll see whether there are chiral carbons or asymmetric carbons present or not. Here we go. So talking about Grignard reagent, we understand Grignard reagent can be prepared by using any of the alkyl or aryl or in fact vinyl halides, and we react with this magnesium in presence of dry ether. So dry ether is basically used as the solvent, so that this in fact, first of all, this is aprotic medium because Grignard is highly basic in nature as well, apart from being nucleophilic. So we cannot afford having any protic solvent like alcohol or things like that, because if we do, Grignard will attack onto that. Even number of aprotic solvents like acetone, DMSO, DMF, they will also be attacked by Grignard, so we cannot afford those reagents as well. The most suitable solvent available for the Grignard reagents turns out to be ether. And although our alkanes are non-polar as well, but in comparison to alkanes, we prefer ether because the Grignard which is being formed is solvated by those ether molecules in the end, so that this becomes fairly soluble in the ethers. Whether we are using normal open chain ethers, we'll find that THF has been preferred choice, which is a cyclic ether, which is much better in such coordination properties in comparison to open chain ethers. So that is how we are preparing it. And during the method of preparation, also there is one point that this goes by free radical mechanism, and that has an implication that if you are having free radical mechanism, there is a possibility of racemization if the carbon was chiral on which this halogen atom was present in the very much beginning. Although that was not the part of a question over here, that may be required somewhere later. Also, we understand whenever we are getting this kind of Grignard reagent formed, there must be no any other functional group present in our Grignard. Because if you dare enough to keep your another functional group present in a Grignard, it is very much possible that this Grignard will be attacking onto that functional group, and you'll be getting some different product rather than the Grignard itself. You will not be in position to retain your Grignard as the final product. That is the idea. Okay, so now talking about the reactions, what we have had here, we have written all the products of these different reactions, and we'll go into details in these reactions one by one. So this is our compound number P which has been formed. This is compound number Q after the sequence of reactions, and this is R, and that is S. So we will see how these products are being formed first, and then we'll come back to the discussion that where chiral carbon are present. You can try checking here itself, but okay, if you check here itself, you'll get the answer directly, but how we are reaching to that product, that is our discussion we are doing about in this video. So starting from the very first reaction, this is the reaction where we started with the cyanide and we have done the nucleophilic reaction on the reagent twice. So twice the nucleophilic reaction starting from a given compound we had done over here. So what was the thought? The first reaction sequence over here, which is generating P, as having twice the attack of Grignard reagent, and both are the nucleophilic attacks only this reaction sequence, and this is followed by acidic workup. So this is going to give you, first this is converting into some ketonic compound, and that ketonic compound is converting into some 3-degree alcohol, as we see happening in the Grignard reagent in general. We'll split this into two parts and we'll talk about one by one. So this is the very first reaction sequence in which our cyanide is being attacked. So in this cyanide, our carbon is having delta positive charge, nitrogen is having delta negative charge. This goes like C triple bond N. Delta positive charge on carbon because of the polarity of this bond is attacked by the Grignard reagent like this. So this bond will be moving towards nitrogen. And this is what we are saying, the carbon is in cyanide is nucleophilic. So this is being attacked by Grignard. And when this is being attacked, we are getting some intermediate imine kind of thing being formed. What that imine looks like. So that is your all remaining group. I am skipping that. So this is going to be C, and there will be attachment of phenyl group, and this double bond being broken to give a single bond. Nitrogen gets a negative charge, so MgBr attaches over here. This is the intermediate imine salt kind of product being formed. If we hydrolyze it, we will be having stages of the hydrolysis. So very first stage, if you don't keep any acidic medium, as happens with the Grignard reagent, we require hydrolysis in almost all the cases. We'll be getting this kind of imine if it was not at all acidic medium plus MgOH-Br. But then when we are having acidic medium present, we understand in presence of acidic medium, imines undergo hydrolysis to get converted into the final product, which is looking as ketone. So what happens in this acidic medium, this nitrogen's lone pair gets protonated by some H+. So now this carbon's nucleophily gets improved upon further. This is being attacked by water in acidic medium. So the intermediate thing over here we can say would have been looking like there is a carbon, there is OH group after loss of H+, there is an NH2 group over here, and this is going to be 1 pH. Now this compound where we are having a tetrahedral carbon, one OH group and one NH2 group, we have seen in a number of different places are not very much stable because of steric demand of these lone pairs which are present, and because these nitrogen oxygen atoms are polyvalent, they will be splitting, they will be decomposing into something else which is going to give you much better, much more stable product where this kind of steric demand is much less. Although going by the thought which is better leaving group, that only should leave, here there is something different. Reaction medium being acidic, NH2 gets protonated in preference. So if this is converting into, like if this is attacking over here, this is converting into NH3+. Now NH3+, which is preferably protonated, would be leaving. Then this oxygen's lone pair will be coming in. You'll be getting C, pH, double bond, O, H+, and there will be NH3 being formed, which immediately gets protonated by the H+ coming from the solution, which is converting into ammoniamine, so that this does not attack back. And because you are having acidic medium, there will be huge number of hydroniamines or H+ ions in water, and ammoniamines number will become equilibrium, will be suppressing these ammoniamines, attacking back to the your whatever that carbonyl compound you have had. Otherwise, you remember reactions of carbonyl compounds with NH2Z, which was happening in acidic medium. This was giving you again these kind of imine products. So there is an equilibrium basically. In this equilibrium now, using large excess of water and H plus ions, we will be converting these things into the aldehydes and ketone rather than going in the reverse interaction. That was the step number, part 1 of the step number 1. Going to the second part, where we'll be having now the reaction of the another Grignard reagent was attacking. So that is the case where this ketone which is formed in the very first step is being attacked by another Grignard. This is we are calling as the traditional Grignard reaction, which we have been knowing from very long time. And in this reaction, this carbon is going to be our electrophilic carbon. So this is going to be attacked by this Grignard PHMGBr. This bond is being shifted away from the carbon, and this attack is going to give us what we are calling as the alkoxide, because this carbon attacked by pH, there is one pH already present, there is one O minus. This alkoxide is being generated by the attack of the Grignard, and this alkoxide we have then done the protonation using water. This time, you remember, whenever we have done the nucleophilic reaction of the Grignard, almost invariably in 99.9% of the reaction, we require protonation either using some protic solvent like water, or we may be requiring some acidic medium like dilute acid. So this alkoxide, what is being generated upon protonation with water, will be giving us the alcohol. What alcohol? It is written over here, right there. So in the beginning, basically this will be alkoxy magnesium bromide, and upon hydrolysis, you can say upon protonation from water, this is the product being formed. There will be some MgOH Br as well produced. Now, if you look at this product, because we were tested about the chiral carbon present, so the alcoholic carbon which is being generated is not chiral at all, because this carbon contains two phenyl groups. Phenyl number 1 came in the first attack, phenyl number 2 came from the second attack of the Grignard agent. So that carbon is not nucleophilic at all. But if you pay attention, the beta carbon, that is the alpha carbon, sorry, gamma carbon, that's the beta carbon, this is the gamma carbon. This gamma carbon contains one ethyl group present on here. This is containing one hydrogen present over here, this one. This also contains one CH3 group present. Actually, this compound should have been written the way CH3, CH2, C, there is one hydrogen, there is one methyl, and then this is CH2, and this is the site of electrophilic attack where we have done all possible modifications, the carbon number alpha, or the last carbon in this reaction sequence, this carbon. So that carbon was not chiral, but what about this carbon? That is alpha carbon, this is beta carbon, this is the gamma carbon. This gamma carbon is lying in our compound starting from the very much beginning. So that carbon is still chiral, and because it was asked whether product P contains a chiral carbon or not, answer was yes, this product contains a chiral carbon, right? Little tricky in the sense where electrophilic attack is happening, that carbon is not chiral. Some other chiral carbon which might have been present from the very beginning is still remaining as such without being affected any longer. Going to the second option, option number B, this reaction sequence was about the Friedel-Crafts reaction in the beginning and Friedel-Crafts acylation, we'll say, and then followed by the Grignard agent. That was reaction sequence generating product Q. So here what we have done, that Friedel-Crafts acylation we had done first, and then we have done the usual traditional Grignard reaction. Acylation is going to give us this compound, and then Friedel-Crafts reaction is going to give us, sorry, the Grignard reaction is giving us the final product. We'll split this reaction into two parts once again, as we have done previously. So what was happening in the case in the Friedel-Crafts acylation, we know in Friedel-Crafts acylation reaction, first of all, acid chloride, what we are having is going to react with the AlCl3. So we say that CH3 double bond OCl is reacting with AlCl3, because AlCl3 is the Lewis acid. This will be pulling the electron from chlorine. This bond is being broken ultimately, so we are getting acyl carbocation, acylium carbocation, sometimes we say, this is being generated and there is AlCl4 minus N present. This is our electrophile. This electrophile is supposed to be attacking the benzene ring in the traditional EAS reaction. We have been seeing that for a quite long time. C double bond O, there is a positive charge over here and there is a CH3. So this reaction is going to give us some aryl carbocation, which aryl carbocation after losing H plus will be converting into the acyl, this benzene, or which we can call as the acetophenone. In fact, this is going to give you double bond O, CH3, there is a positive charge, there's hydrogen, double bond, and then this hydrogen loses its H plus to AlCl4 minus in the last step, so that you are getting the benzene ring intact. There is a question here. Actually, that question is not so relevant, but some of the students think why this is attacking, why electrophile is attacking onto the benzene ring. That is very much obvious because the benzene ring is very much electron rich. And why it is electron rich? We use this terminology sometimes that these 6 carbons put together, they are a sandwiched, like they are kind of a sandwich of these 6 electrons. The 6 carbons present in the benzene ring are having the electron density of the 6 carbons, in which it is forming kind of a sandwich structure. You can possibly visualize it in this way. There are 6 carbons of the benzene ring like this, and onto these 6 carbons there are electron density, like these pi bonds which are present over there. All these pi electrons present over here are forming one electron rich region, and there is this electron density present in the below region as well. So if that yellow part of the benzene ring, what I try to show is going to be kind of your one particular plane that has been sandwiched by the layer of electrons at the top, layer of the electrons in the bottom. That is what is we are considering it as sandwich. Because this is surrounded by the electron rich things, this is preferably attacked by the electrophiles, which are electron poor compound. So this reaction sequence is generating a compound what we are calling as acetophenone. This is the compound called acetophenone. Now in the next step, this acetophenone is undergoing again that what we have called as traditional Grignard reaction, and that is going to give you the alkoxide. Acetophenones, this carbon will be attacked by this thing. So we'll be getting the same way alkoxide, and then alkoxide again will be getting protonated by the water as the solvent, and that is going to generate this 3-degree alcohol. This carbon is 3-degree. Now again, here we are having one phenyl and another phenyl. So compound number Q this time again cannot be chiral. Actually, this time the whole compound is not chiral at all. That product number P, because there is no other chiral carbon left, and this carbon is not chiral at all. So this is your A chiral, which means there is no asymmetric carbon present. This is symmetric product. So Q will be having no chiral carbon. Moving on to the next option, here we are having the acid chloride started from the beginning we have taken. Here we have 2 different kind of reactions. Number 1, we are reacting with the dialkyl cadmium with the acid chloride, first step, and then we are reacting the aldehyde or ketone generated with the Grignard reagent again. So coming to this first point, when we are using the dialkyl cadmium, what will be happening? This dialkyl cadmium, what we are having is basically a distant cousin of the Grignard reagent, and we understand that Grignard reagent is very much reactive because R is bonded to magnesium over there. So here the magnitude of delta negative charge on carbon is very high in comparison to the magnitude of this delta negative charge on the dialkyl cadmium. And reason lies in the relative reactivities of these groups. So this delta negative charge on the cadmium is relatively less. So we'll understand this is going to be relatively much stronger nucleophile, and this one is going to be relatively much weaker nucleophile. So this weaker nucleophile can attack very highly reactive compounds. Highly reactive acid chlorides, RCOCl, are attacked other groups like aldehydes, ketones, esters, amides, those things are not attacked by the dialkyl cadmium. That is the speciality of this dialkyl cadmium. That's what we are using. We are saying this thing that the dialkyl cadmiums are mild and selective reducing agents. So they will be reducing only few compounds. They cannot reduce everything available. In contrast to the Grignard reagent, which is this much strongly nucleophilic, this will not spare any polar group, in particular any polar multiple bonds. Polar single bonds, some of them are also being attacked, but any polar multiple bond present, Grignard is bound to attack over there, irrespective of the identity of the elements. Okay, so this thing, when we are reacting either your acid chloride as RCOCl or ArCOCl, this will be converting into the ketonic compounds, and now this ketonic compounds which is being generated can be reacted further in different reactions. This ketone which is being generated, we are calling this compound as phenyl acetone, because this would have been acetone and there is one phenyl group present. So in this phenyl acetone, further attack of dialkyl cadmium is not going to happen because this is not that reactive. The dialkyl cadmium is relatively much weaker nucleophile. Cadmium was much lower in the reactivity. It was much less electropositive in comparison to magnesium. So the polarization, or you can say the polarity in the carbon cadmium bond is much less in comparison to polarity in carbon magnesium bond in the Grignard. So that gives a condition that this reaction will stop at this particular place only. And if you look at the JEE, the way they have framed this question, they have given here that we have used only 0.5 equivalents of, that's half equivalent of the dialkyl cadmium, so that if you have taken only 1 mole of this acetyl chloride, you will be having, by the time 1 mole of this phenyl acetone is formed, you will be exhausted with your dialkyl cadmium. No further reaction is possible. Actually, even if it was present in more than 0.5 equivalent, then also we expect further reaction would not have taken place. Our final compound ketone only would have been obtained if temperature is not kept very high, like less than normal temperature. If you are keeping, you can stop this reaction very selectively at that particular point. Okay, moving on to the second step of this option, we are this reaction sequence. We are having here this phenyl acetone is the starting compound now, and this phenyl acetone is now being attacked by the Grignard reagent. That is again the traditional Grignard reaction. We have seen this number of times already, and this traditional Grignard reaction, this phenyl acetone is electrophilic carbon, so this phenyl group is attacking over here, and this will be converting into some alkoxide, and alkoxide will be generating some tertiary alcohol as we have seen in the previous sequence. But here there is something which is now different than the previous case. This product R in this sense now, in the sequence now, is having 3 different groups. One is methyl group, another one is your phenyl group, and another one is over here benzyl group. All the 3 groups in this tertiary alcohol are now different. So this classifies to be a chiral compound. There is no, this product, okay, we are not talking about Q, now we are talking about R. Product R has chiral carbons present, so we are having here chiral carbons present now. This is going to be the correct option with respect to if asymmetric carbon are present or not. Okay, so moving further, now we are having the fourth reaction sequence in which we are getting the compound number S being generated. This was a little lengthier than the previous sequences because here we have used 4 different reagents. We have used Grignard, CrO3, HCN, and then H2SO4. So what all these reaction sequences imply? In the first reaction sequence, we are doing Grignard reaction. We are getting this alcohol as usual, this one. And in the second reaction sequence, when in the second step of this reaction sequence, when we are doing oxidation, this what you call 2-degree alcohol is being converted into some ketonic product, and then further this ketone is undergoing cyanohydrin, addition of HCN is happening basically there, and this addition of HCN is going to give us what we are calling as nucleophilic addition. That generates this compound called as cyanohydrin. And the last step, where sulfuric acid, hot Dehydration, they actually did not tell us that this is concentrated sulfuric acid. But if it is sulfuric acid and you are keeping heat present and you are having some alcohol, and that alcohol too is 3 degree, there are fair enough chances that dehydration will take place and we'll be getting some unsaturated compound being formed. We'll see these options one by one. Here we go. The very first reaction, that was about the attack of the Grignard reagent onto the some aldehyde. So this is again some traditional reaction in which this alkoxide will be formed in the first place, and then protonation of that alkoxide which is there is going to give us again all the 3 alkyl groups are different, so this is going to be the chiral. But this is not the final product S. This is much before S. We can say maybe S1. Let us say this was S1. This is not the S product final. This was chiral. They did not ask about S1. They asked about the final product. So this is the second part of that reaction sequence in which we are having the oxidation taking place. So when we are doing oxidation with CrO3, this is a 2 degree alcohol, and these 2 degree alcohols are supposed to be oxidized using, this is very strong oxidizing agent, that dilute H2SO4 we are using in presence of CrO3. This is oxidant, and this is, we should say, strong oxidant. Although it is strong, if you are not using heat over there, the ketones which are being formed will not further be oxidized. If we are using heat as well, these ketones which are generated may further be oxidized, and we could have got the corresponding carboxylic acids as the final product. No heat being given, we'll understand reaction will stop at this particular stage only, where the ketones are being formed. This time our ketone is benzyl phenyl ketone. So 2 different groups are present. One is benzyl group and one is phenyl group, as coming from the previous reaction sequence. Phenyl was added into the last reaction where Grignard has attacked. And now this product is achiral because you don't have any, this carbon is no longer sp3 hybridized, and earlier it was this compound, this starting compound over here was chiral, but the product, let us say this is S2 product, this has become achiral because that chiral carbon is lost during the oxidation step, right? Okay, the third reaction of this sequence is now you are reacting with HCN. So actually the kind of a whole bunch of reactions in organic chemistry they have tested in the single reaction. That was quite time taking paper in chemistry, although there were not too many complicated reactions, but there were a huge number of reactions in many of the questions. You will see if you have solved that paper already, you realize that you know it very well, and you have done actually that in the examination hall. That is kind of very long lasting thing, and that gives you the real feel how long this reaction will be taking in the exam. Okay, so this is the last reaction where we are having the carbonyl compound, and this is being attacked by the nucleophile. Basically, this is a reaction of the aldehydes and ketones where the nucleophilic addition of HCN is taking place. So HCN, actually we don't use as such. We are using this in 2 parts. Number 1, we are doing protonation of this oxygen lone pair. That is how we are doing this reaction. In fact, we are using some source of acid, and then we are using some source of cyanide, because HCN is not very much acidic, not very much nucleophilic. So direct HCN is not gives you this reaction very easily. Going by the thought, by the understanding what they want to ask, we'll think that way. So this oxygen will get protonated, then this carbon will become more nucleophilic, and then the cyanide ion will be attacking from here. That is how this reaction happens, and that is giving us this benzyl group BHCH2 as such intact. There's phenyl group as such intact, and therefrom cyanide is attacking, and here we are getting this OH thing. So this is the new carbon-carbon bond formation taking place in this particular step that we have shown over here. This is our product number S3. This is again chiral, but this is again not the final product. This is kind of there as playing hide and seek in this question with respect to the chiral carbon. If you see the very first product formed S1 was chiral. Upon oxidation, the second product formed was achiral, and now upon reaction with HCl, this product is formed again chiral, and in the next step when we are doing reaction with sulfuric acid, again it is achiral. So chiral, achiral, chiral, achiral, it's kind of a game of hide and seek to me. So that is what was happening. Again, the chiral carbon is being generated when we are having the cyanohydration, cyanohydrin formation taking place. Now, the last part of this reaction sequence, fourth, is where we are reacting with the concentrated sulfuric acid. A little bit tricky it was, and in fact, if you just try to see whether chiral carbon is present or not, that was not at all tricky. But this is a little bit tricky in the sense when we are saying that cyanohydrin, which is having one cyanide group and one OH group present at the same carbon, this cyanide group actually undergo hydrolysis in presence of H2SO4 if temperature is kept higher. We recall this from the preparation of amide. If it was cold concentrated sulfuric acid, we get amide as the major product. But if you increase the temperature, if temperature is kept higher, the amides which could have been generated are CuNH2, they are further hydrolyzed. If this is acidic medium, these compounds are further hydrolyzed and we get ultimately RCOOH and NH3 plus, rather NH4 plus. These products we get at higher temperature in presence of sulfuric acid. So the very first thing what we should expect is, although dehydration is going to happen, but before dehydration only, this is expected that hydrolysis of cyanide group will also take place because we are having very, very acidic medium present, sulfuric acid, and temperature is also high. So before dehydration of this OH starts taking place, we expect cyanide would also undergo hydrolysis into carboxylic acid group. And by same time, in presence of heat, this oxygen also gets protonated. So if this oxygen is getting protonated by the hydrogen coming from, okay, we should have written it a little bit different place because there is some more text appearing from the top. So if this oxygen is being protonated, say by H plus, now this oxygen, this whole group is now becoming a good leaving group. We understand that whenever we are having the OH group being protonated either by some regular Bronsted acids or some Lewis acid, this converts into good leaving group. So when that will be leaving, you will be getting here some carbocation generation possibility. Whether it was cyanide present in the beginning or it was the carboxylic acid present in the beginning. Getting a full-fledged carbocation is something which we expect is going to be less likely, and that is why we are emphasizing here this reaction is going to be kind of in E2 fashion, which is going to give us the attack of the H plus and attack of HSO4 minus ion happening side by side. There will be some HSO4 minus ion present in this reaction medium, which can be pulling this one of the, this is the alpha carbon, this is the beta carbon. From alpha carbon as OH2 protonated alcohol will be leaving at the same time from this beta carbon over here, HSO4 minus ion will be pulling this acidic hydrogen from the beta carbon, and we will be getting a double bond being generated over here. This double bond will be generated. Again, I am emphasizing this is going to be most probably E2 fashion, because if you want to have this as even mechanism will be requiring the stabilization of the carbocation which would have been formed. Stabilization of carbocation would have been possible if there was actually this phenyl group will be stabilizing the carbocation which could have been generated, but this cyanide in the beginning, whatever it was present, it is way stronger minus M effect. This will be destabilizing it up to much greater extent. Even if this is converted into carboxylic acid group, that is also having quite electron withdrawing effect that may not help the carbocation get stabilized. And rather than thinking that, because we know that 3-degree alcohols, when we bring them into this elimination reactions, they can, rather than being even, they can go E2 mechanism if there are not very stable carbocations being generated. So because the transition state, which can be over here, which can be relatively electron rich, can be stabilized by this electron withdrawing group. That is a favor for the E2 mechanism or disfavor for the E1 mechanism. So, okay, we expected this reaction to give you some double bond present, although E1 and E2, if you compare, the E1 is going to be very, very less likely. E2 is going to be favored under the reaction sequence, which is given here. Okay, moving further, we have got the reaction here, which was going to give us no chiral carbon present. There was one more possibility over here if the double bond was not being formed over here. If it was what we have seen in the concentrated sulfuric acid in other reaction sequences, that was if there is a benzene ring over here. There is a benzene ring over here, and we are having some CH2 group over here, and then this is your COH, pH. COOH converts into carboxylic acid group, something like this. Then this OH2 can get protonated, and we have now a possibility of getting this carbocation generated. And this carbocation, as we have seen in the previous cases, can be attacked from this ortho position as well, giving you something like this. But that possibility would have happened if we would have taken concentrated sulfuric acid, where this compound could have been chiral. This possibility we are ruling out, because for that we would have definitely required concentrated sulfuric acid, which can deprotonate already acidic carboxylic acid, COOH. So this deprotonation will be requiring concentrated. Because they had not given it, we will be ruling out that possibility. We will be thinking with respect to the way dehydration of that alcohol may be taking place either in SN1 fashion or in SN2 fashion. Okay, so now this compound, what we are having is this is product number S. This is having no chiral carbon left. So that is all the reaction sequences what we have seen as of now. PQRS, once again we can have a look. These were the compounds PQRS. So in compound number P, that is not the chiral carbon, but here is the chiral carbon present. Compound number Q, no chiral carbon present. Compound number R, there was a chiral carbon present. Compound number S, no chiral carbon present, although this is now a stereocenter for geometrical isomerism, because double bond contains one side hydrogen, one side phenyl, one side phenyl, one side COOH. That could have shown geometrical isomerism, but they asked for asymmetric carbon. That is not there. So looking at the options, now there is no confusion left. Which option should be correct? Here we go. The correct options were C and D. You can see that by yourself. I think that was a very, very long discussion. Hopefully you have seen every single point in much, much greater detail, which you could have possibly anticipated from this video. And if that was well to your expectation, I hope you may like and subscribe to this channel so that I get inspiration of doing more such videos. Thank you. Bye-bye. Take care. Stay tuned. See you in the next video very soon for the question number 3 of this same section, paper number 1.